This is going to be a review of colligative properties and the calculation of molar mass from freezing point and boiling point data. To remind you, colligative properties are properties that depend on the number of solute particles dissolved in a given mass of solvent. Again, these solute particles must be non-volatile. That is, they themselves cannot want to form a gas. They must remain a solid. So things like salts are non-volatile, things that are not going to vaporize themselves. And three important colligative properties I expect you to know are boiling point elevation, freezing point depression, vapor pressure lowering. When you make a solution with a non-volatile solute, it makes the boiling point of the solvent go up, it makes the freezing point of the solvent go down, also lowers the vapor pressure of the solvent. One of the things I'm going to expect you to be able to do is to distinguish between those solutes that will and will not have a colligative effect. For example, which of the following solutes would not raise the boiling point of water, a solvent such as water? The answer here are both 3 and 4. These are volatile substances. Again, volatile meaning they want to become a vapor or a gas. Acetone has a strong odor and therefore tends to vaporize or is volatile. Nitrogen is normally a gas at room temperature, so it is volatile. The idea here is this: if I have a solvent and I start to heat that solvent, then any nitrogen that is dissolved is going to leave. Any acetone that is present is going to leave. As soon as I start heating it, because these are volatile, they tend to vaporize, and in the case of water, which boils at 100 degrees Celsius, by the time you heat it that hot, there is no more nitrogen, there is no more acetone left, and it is pure water, so it will not raise the boiling point of water. Which of these aqueous solutions would have the lowest freezing point? The answer is the one that produces the greatest number of particles. That is what colligative properties depend on, is the number of particles. The equation is the same for all three, A, B, and C. The change in the freezing temperature is the molar freezing point constant times the molality. The molality is the only thing that is going to vary here. Note, we start with the same molar concentration of both A, B, and C. B, however, is a molecular compound. Molecular compounds do not dissociate, so that stays at a 1.0 molar concentration. A and C, however, are ionic compounds that do dissociate. Sodium chloride dissociates into a sodium ion and a chloride ion. Calcium chloride dissociates into a calcium ion and 2 chloride ions. And so for every 1 mole of sodium chloride, I get 2 moles. So effectively, that's a 2.0 molar concentration. And for calcium chloride, I get 3 moles. So multiplying that by 3 is going to give me a 3.0 molar concentration, giving me the highest molar concentration, therefore the highest colligative effect. So C would be the correct answer for the first one. For the second one, for the sodium chloride, I am going to get 2 ions, so multiplying that by 2 is going to give me a 4.0 molar concentration. B is a molecular compound, so that is going to stay a 3.0 molar concentration. Calcium chloride is going to give me 3 ions, so multiplying that by 3 is also going to give me a 3.0 molar concentration. So A has the greatest number of particles, the greatest molar concentration of particles, therefore is going to have the greatest colligative effect. To remind you how to calculate freezing point depression from this data, again, the change in the freezing temperature equals the molar freezing point constant times the molality. Now you're given a 25% solution of methanol. This is a non-volatile, non-electrolyte, or is a non-electrolyte substance. It has a molar mass of 32.05. And we're just going to take the molar freezing point constant, which is 1.86, multiply it by its molality. Note I have 25 grams of solute and 0.075 kilograms of solvent. Where did those numbers come from? When you're given a percent solution, assume you've got 100.0 grams of the solution, and that then is going to give me in a 25% solution 25.0 grams of the solute. And if I have 25.0 grams of the solute, I must have 75.0 grams of the solvent. And so that's where that number of grams comes from. That's where that number of kilograms comes from. And I change grams to moles by dividing by the molar mass, and that gives me 19.3 for my change in the freezing temperature. The final answer is going to be at negative 19.3 degrees Celsius, remembering that the colligative effect for freezing point is freezing point depression, makes the freezing point go down. Calculate the molar mass from freezing point or boiling point data, I'm going to use the exact same equation. The change in the freezing temperature equals the mole freezing point constant times molality, or it could be the change in the boiling temperature equals the mole boiling point constant times molality. Note the setup here is exactly the same as the previous problem, only now I'm told the change in the freezing temperature. Water normally freezes at 0. This solution is freezing at a negative 0.89, so that is my change in the freezing temperature. Now I want to solve for the molar mass of the solute, and so that is the number that I am solving for. And the rest of this is math. If you want to see how the math is done, here's the same equation. The first thing I'm going to do here is try to get rid of this 1.86. So to do that, I'm going to divide both sides by 1.86. That's going to eliminate it from this side and leave just this on the right-hand side. And so that is going to give me this equation. 0.89 divided by 1.86 is going to equal 4.78. Now I need to get rid of this 0.5, so I'm going to multiply both sides by 0.5. That is going to get this to cancel out, leaving just this, and that times 0.5, which is going to give me 0.239 equals 22.5 over times 1 over x. Now I'm going to divide both sides by 22.5, giving me this. Rearranging this equation to solve for x. X is going to equal 1 mole over 0.0106, which gives me a final answer. X equals 94 grams per mole. If you wish to check and make sure you're correct, you can go back to the original equation, plug in 94 grams per mole, making sure that you get an answer of 0.89 degrees Celsius. Thank you for watching.